Welcome to Talk Tensors, everyone. The show where we like to really get down into the weeds of some of the most interesting machine learning papers out there. Today, we're taking a deep dive into a paper that's trying to bridge a pretty fascinating gap in AI, the one between logic and actual learning. It's called Hierarchical Neuro-Symbolic Decision Transformer. And just the title alone has got me thinking we're in for quite a ride with this one.
Yeah, no, this paper is definitely ambitious. It's taken on a real challenge, trying to combine those strengths of symbolic AI, the one that excels at planning and all that logical reasoning, with the kind of adaptability we see in neural networks, which are really great at learning from data. It's like trying to take the best of both worlds, right? And I think the authors have come up with a really intriguing approach for it.
Okay, so before we dive into all the nitty-gritty, can we rewind a little bit? Why is this whole idea of combining symbolic AI and neural networks such a big deal? I mean, it sounds a bit abstract.
It's a big deal because it really gets to the core of what we want AI to be able to do. Imagine self-driving cars. You've got these cars that need to follow traffic rules. That's the logical symbolic part. But then they also need to react to these unexpected events, like, say, a pedestrian suddenly decides to cross the street. That requires flexibility, requires learning capabilities that you typically find in a neural network.
So it's like you've got a rule book, but also knowing when to kind of throw it out the window and just improvise.
Exactly. Traditional symbolic AI is great when you have well-defined problems, nice, clear rules. But the real world, it's messy, it's unpredictable. And that's where symbolic AI struggles. Neural networks, on the other hand, they're great at adapting, but the problem is they can be difficult to interpret. It's hard to understand why they make the decisions they do. And that can be a real problem when you're talking about things like self-driving cars, where you've got these, life or death choices being made.
That makes a lot of sense. So how does this paper try to solve this whole conundrum? What's their secret sauce?
Their secret sauce is really this hierarchical system they've come up with. So imagine you have an architect creating a blueprint. That's like the symbolic planner in this system, laying out that high-level plan. But a blueprint isn't the same as a building, right? You need skilled workers to take that plan and then actually construct that building. And they have to adapt to any unforeseen challenges along the way.
Okay, I'm starting to see where you're going with this. So the construction crew, that's like the neural network, taking that symbolic plan and then translating it into real-world actions.
That's it. And what they use is something called a decision transformer. It's a specific type of neural network that's particularly good at handling these sequences of decisions. So the decision transformer takes those symbolic instructions from the planner and it turns them into smooth, reactive actions, just like a construction crew making adjustments on the fly as they build.
So they're not just saying combine symbolic AI and neural networks. They're actually proposing a concrete architecture for how to actually do it.
Right. And what's really cool is that this hierarchical approach isn't just some theoretical idea. They've actually tested it out. And the results are pretty compelling. They design what are called grid world environments. Just think of them like simple video game levels. You've got keys, locked doors, items to collect. You get the idea.
So classic adventure game stuff, but for AI research. I like it.
Exactly. And their hierarchical system, with that combination of symbolic planning and the neural network execution, actually consistently outperformed agents that rely just on neural networks. And this is especially true in tasks that require these complex multi-step sequences. We're not talking about a small improvement either. This is a significant jump in performance.
So it sounds like this hierarchical approach really could be a key to unlocking more robust and even intelligent AI systems. But hold on, you mentioned earlier that the paper also gets into some pretty heavy math. What's that all about? Why does the math even matter?
Well, in machine learning, it's not enough to just show that something works. You want to understand why it works. What are the limitations? How can we potentially improve it? And that's where all the math comes in. The authors do this really deep theoretical analysis, looking at how errors from both the symbolic planner and the neural network could potentially accumulate.
It's like trying to figure out the margin of error in a complex engineering project, right? You need to know how reliable the system is and also where potential weaknesses might be.
Precisely. Yeah. And they were able to come up with these mathematical bounds for how much the system's performance could deviate from that ideal plan, which is crucial for understanding the reliability and safety of such a system, especially if you're thinking about real-world applications. I mean, it's one thing to have a robot solve a puzzle in a simulated environment, but it's another thing entirely to trust it to perform surgery or drive a car.
Okay, so we've got this cool new architecture, impressive results, some solid mathematical grounding behind it. To put this in perspective, can we take a step back and look at the history of ideas that led to this paper?
That's a great idea. I mean, this paper didn't just come out of nowhere. It builds on decades of research in symbolic AI, reinforcement learning, and more recently, transformer-based models. So why don't we start with symbolic AI? It was all the rage in the early days of artificial intelligence. The focus was on logic and that formal reasoning. Think of programs that could solve logic puzzles or play games like checkers.
Right, but those systems were often pretty brittle, like they couldn't really handle the messiness of the real world, could they?
Exactly. The real world is full of noise, full of uncertainty, and that really throws a wrench into that neat, logical world of symbolic AI. And that's what led to the rise of other approaches like reinforcement learning.
Yes, reinforcement learning. That's where agents learn through trial and error, right? Sort of like training a dog with treats.
You got it. Instead of relying on those pre-programmed rules, reinforcement learning agents learn by interacting with their environment and getting feedback through rewards or penalties. And this approach has been incredibly successful in areas like game playing, robotics, even recommender systems.
So reinforcement learning was this big step forward in terms of AI's ability to adapt and learn. But I imagine it has its own challenges as well, right?
Of course. I mean, for one thing, designing those effective reward functions can be tricky. You have to be very careful about what you're actually rewarding the agent for. Otherwise, you might get unexpected, even undesirable results.
That makes sense. You don't want your AI system optimizing for the wrong thing.
Exactly.
Yeah.
And then you also have the issue of training. Reinforcement learning can be computationally very expensive and often requires huge amounts of data. So you've got symbolic AI, which is logical but inflexible. And then you've got reinforcement learning, which is adaptable but could be difficult to train and control.
And then along came transformers. Those are the new kids on the block, right? The ones that have revolutionized natural language processing.
That's right.
Transformers were initially designed for handling language, but their ability to process that sequential data and capture those long-range dependencies has made them incredibly effective in a whole range of tasks, including, as we see in this paper, control problems. So how did researchers get the idea to combine these seemingly very different approaches? Symbolic AI, reinforcement learning, and transformers.
Well, the idea of combining the strengths of different AI approaches has been around for a while. Researchers recognized early on that each approach had its limitations. And maybe, just maybe, they could achieve something truly remarkable by blending them together.
It's like they were trying to create the ultimate AI fusion dish, taking the best ingredients from all these different culinary traditions.
I like that analogy. But finding the right recipe, that right way to blend these different approaches, has been a major challenge. Some early attempts involve using symbolic rules to guide the learning process in reinforcement learning, or using symbolic reasoning to try to interpret the output of neural networks.
So sort of like using symbolic AI as a coach for that reinforcement learning agent or as a translator to help us understand what the neural network is thinking.
Exactly. But these approaches often felt a bit like a patchwork, not a truly integrated system.
And that's where this paper comes in, right? Proposing a more elegant and unified framework with this hierarchical system of symbolic planning and decision transformation.
Precisely. And they didn't just stop at the architecture. They also did some serious math to back up their claims, providing a deeper understanding of how those errors propagate through the system.
Which is essential for building trust and ensuring the reliability of such hybrid AI systems, especially if we're thinking about real-world applications.
Absolutely. Now, I know you're eager to get to the novel notion section, but before we do, I think it's important to emphasize that this paper isn't just about building a cool new AI system. It's about laying that theoretical groundwork for a more robust and interpretable approach to artificial intelligence. It's about understanding the why behind the what, which is essential if we want to move beyond just building systems that work to building systems that we can understand and trust.
Okay, I'm sold. This paper is a big deal. So let's get to the fun part. What are some of the potential research directions or even open questions that this paper sparks? What are the novel notions that are swirling around in your head?
Well, one thing that really struck me was how well this hierarchical approach seems to work in those grid world environments.
Yeah.
I mean, they're fairly simple, but they do capture that essence of planning and sequential decision making. It just makes me wonder, what if we could scale this up to something way more complex?
That's a fantastic question. And you've hit on one of the most exciting avenues for future research. What if we could take this hierarchical system and apply it to a game like Minecraft?
Minecraft. That's a brilliant idea. It's a game with almost infinite possibilities. It requires creativity, planning, resource management, even social interaction if you're playing with others.
Exactly. Imagine having this hybrid AI that can not only strategize like a pro gamer, mastering combat and resource gathering, but also showing genuine creativity in building these elaborate structures, maybe even collaborating with human players in some really meaningful ways. That's mind-blowing. It would be like playing alongside an AI that's both a brilliant strategist and an imaginative architect. But how would this really push those boundaries of game AI? Wouldn't it just be a really, really good Minecraft player?
It's about more than just winning the game. It's about creating these AI agents that exhibit a much deeper understanding of that game world, its rules, its possibilities. Imagine an AI that could actually grasp that concept of beauty or efficiency in its designs, or one that could come up with these novel solutions to in-game challenges that human players haven't even thought of.
So it's about creating AI that can actually surprise us with its creativity and its ingenuity. That's a far cry from the AI opponents we're used to, who often feel predictable and limited. This could lead to entirely new gaming experiences where the line between player and designer becomes blurred.
Precisely. And think about the potential implications beyond gaming. If we can create AI that can truly understand and interact with these complex virtual worlds like Minecraft, what does that tell us about the possibility of AI interacting with the real world in more meaningful and sophisticated ways?
That's a profound thought. It's like Minecraft could be a testing ground for AI that could eventually design buildings, solve engineering problems, or even navigate social situations in the real world. But let's not get ahead of ourselves. Even just getting an AI to play Minecraft at a human level would be a remarkable achievement.
It would indeed. And it wouldn't be easy. Minecraft presents this unique set of challenges for AI. You've got that open-ended nature, that complex crafting system, and the need for both long-term planning and real-time adaptation. But that's what makes it such an intriguing research problem. It would require pushing those boundaries of what's currently possible with AI, and the insights gained could have some far-reaching implications.
You've given us, and hopefully our listeners, a lot to think about today. This paper on hierarchical neuro-symbolic decision transformers is clearly a significant step forward in AI research, and the potential applications from robotics to self-driving cars to even scientific discovery are incredibly exciting.
Indeed. It's a reminder that we're living in an era of unprecedented progress in AI, and the future is full of possibilities.
Well said. And to all our listeners out there, if this paper has sparked your curiosity, we encourage you to check it out for yourselves. You'll find a link in the episode description.
And if you come up with any novel notions of your own, be sure to share them with us. We're always eager to hear from our listeners.
That's all for this deep dive into the world of hierarchical neuro-symbolic decision transformers. Until next time, keep those algorithms humming.
You know, one thing that really got me thinking was just how well this hierarchical approach seems to work in those grid world environments. Yeah, they're simple, sure, but they do capture that essence of planning and, that whole sequential decision-making thing. And it makes me wonder, what if we could take this and scale it up to something much more complex?
Oh, that's a great question. And you've really hit on one of the most exciting avenues for future research here. Yeah. I mean, what if we could take this hierarchical system and apply it to something like a game like Minecraft? Now, that is a brilliant idea. It's like this game with almost infinite possibilities, right? You need creativity, you need planning, you need resource management, and even social interaction if you're playing with others.
Exactly. Just imagine a hybrid AI that could not only strategize like some pro gamer, mastering combat, mastering resource gathering, but then also show genuine creativity, like building these really elaborate structures, maybe even collaborating with human players in some really meaningful ways.
That's just mind-blowing to think about. It would be like playing alongside an AI that's both a brilliant strategist and this imaginative architect. But wouldn't this just make a really, really good Minecraft player? How would this really push the boundaries of game AI?
Well, it's about more than just winning the game, you see. It's about creating these AI agents that can exhibit a much deeper understanding of that game world and all of its rules and all of its possibilities. Imagine an AI that could actually grasp concepts like beauty or efficiency in its designs, or even come up with these novel solutions to in-game challenges that we as human players haven't even thought of.
So it's about creating AI that can actually surprise us with its creativity and its ingenuity. That's a far cry from the AI opponents we're used to, right? The ones that often feel kind of predictable and limited, this could lead to entirely new gaming experiences where the line between player and designer starts to blur.
Precisely. And think about what this could mean beyond gaming. If we can create AI that can truly understand and interact with these complex virtual worlds like Minecraft, what does that tell us about the possibility of AI interacting with the real world in more meaningful and sophisticated ways?
Now, that's a profound thought. It's like Minecraft could be this testing ground for AI that could eventually design buildings, solve engineering problems, or even navigate social situations in the real world. But let's not get too ahead of ourselves. Even getting an AI to play Minecraft at a human level would be a huge achievement.
It would indeed, and it wouldn't be easy. Minecraft presents a really unique set of challenges for AI. You've got that open-ended nature, you've got that complex crafting system, and then the need for both long-term planning and that real-time adaptation. But that's what makes it such an intriguing research problem. It would require pushing those boundaries of what's currently possible with AI, and the insights we gain could have some very far-reaching implications.
Well, you've definitely given us, and hopefully all of our listeners out there, a lot to think about today. This paper on hierarchical neuro-symbolic decision transformers is clearly a big step forward in AI research. And the potential applications from robotics to self-driving cars to even scientific discovery, it's all incredibly exciting.
Indeed. It's a great reminder that we're living in an era of unprecedented progress in AI. The future is full of possibilities.
Well said. And to all our listeners out there, if this paper has piqued your interest, be sure to check it out. We'll include a link down in the episode description.
And if you have any of your own novel notions, be sure to share them with us. We're always happy to hear from our listeners.
That's all for this deep dive into the world of hierarchical neuro-symbolic decision transformers. Until next time, keep those algorithms humming.